Hello Matrix. Let's talk about efficient large-scale language modeling with a fascinating concept known as mixtures of experts. This intriguing approach will help us unlock the potential of our language models, so stick around to find out how. To understand mixtures of experts, we need to familiarize ourselves with two concepts, experts and gating networks. Think of experts as specialized teams within a company. Each team is really good at a particular job. For instance, the marketing team is great at promoting products, the finance team excels at managing budgets, and so on. In the context of a neural network, each expert is a mini neural network that's good at modeling a specific part of the data. For instance, one expert might be good at understanding sports-related text, another might excel at medical text, and so on. Now, having a bunch of experts is great, but how do we decide which expert to use for a given piece of data? That's where the gating network comes in. The gating network is like a manager who knows the strengths of each team, expert, and assigns tasks, data, to them based on their strengths. The gating network takes the input data and computes a set of weights for the experts. These weights determine how much each expert contributes to the final output. If an expert has a high weight, it contributes more to the output. If an expert has a low weight, it contributes less. Now, you might be wondering, why go through all this trouble? Why not just use a big, single neural network for everything? Well, the beauty of the MO approach is that it allows us to effectively train much larger models. Each expert is a relatively small model, and we can have many of them. But since only a few experts are active for each piece of data, the computational cost is much less than that of a single large model. So, in a nutshell, a MO model is a kind of ensemble of expert networks, managed by a gating network. This setup allows us to model diverse data more effectively and efficiently than a single large model. Let's delve deeper into how these models are trained. Training a MO model is a bit more complex than training a regular neural network, due to the presence of the gating network and multiple experts. But the fundamental principle remains the same: we want our model to make as few errors as possible. We train the model by showing it lots of examples and adjusting the parameters of the experts and the gating network to minimize the errors. But here's the twist: since the gating network decides which experts to use for each piece of data, the training process also involves learning these gating decisions. So, how does the model learn to make good gating decisions? Well, it uses the errors made by the experts to guide its decisions. If an expert makes a lot of errors on a particular type of data, the gating network learns to assign less weight to that expert for similar data in the future. On the other hand, if an expert does well on a certain type of data, the gating network learns to assign more weight to that expert for similar data. This dynamic between the gating network and the experts is what makes MO models so powerful. The experts become more specialized over time, each becoming really good at modeling a certain type of data. And the gating network becomes better at deciding which experts to use for each piece of data. But the training process isn't all smooth sailing. One challenge with MO models is what's known as the rich get richer problem. In the early stages of training, some experts might get lucky and do well on the data they see. The gating network then assigns more data to these experts, which makes them even better. This can lead to a situation where a few experts get all the data, while the rest are left out in the cold. To prevent this, MO models use a technique called load balancing. This involves adjusting the gating network's decisions to ensure that all experts get a fair share of the data. This way, all experts get the chance to learn and improve, leading to a more diverse and robust model. Let's delve into the benefits and challenges of MO models in handling different types of data. MO models excel at modeling diverse data because of their structure. Remember, each expert in the model specializes in a certain type of data. So, if we have a lot of diverse data, the experts can divide and conquer, each modeling the part of the data it's best at. This is particularly useful in language modeling. Language is incredibly diverse, with different topics, styles, and nuances. Having different experts specialize in different aspects of language allows the model to capture this diversity much better than a single, large model could. However, this doesn't mean that MO models are perfect. One challenge is that the quality of the model's output depends heavily on the gating network's decisions. If the gating network assigns a piece of data to the wrong expert, the model might produce a poor output. This challenge is exacerbated when the model encounters data that's very different from what it has seen before. In such cases, the gating network might struggle to decide which expert to use, leading to suboptimal outputs. This is a common challenge in AI, known as the problem of out-of-distribution data. To mitigate this, some MO models use a fallback mechanism. If the gating network isn't confident in its decision, it can defer to a generalist expert. This expert is trained on all types of data and can provide a reasonable output when the other experts can't. In a nutshell, while MO models can handle diverse data effectively, they also have to grapple with the challenges of out-of-distribution data and the dependency on the gating network's decisions. But don't worry, researchers are actively working on ways to overcome these challenges and improve the capabilities of MO models. And there you have it, a deeper look into the workings of MO models. Now let's discuss the kind of results they can achieve and what it means for the future of AI. MO models have shown promising results in a variety of tasks. In language modeling, for instance, they have achieved state-of-the-art results, outperforming single, large models. They've been able to generate high-quality, diverse text that captures the nuances of different styles and topics. These results are exciting not just because they're impressive, but also because they open up new possibilities for AI. With their ability to model diverse data effectively, MO models have the potential to make AI more versatile and useful in a wide range of applications. From more accurate translation systems to more engaging chatbots, the potential applications are vast. But the journey doesn't end here. There are still challenges to overcome and improvements to be made. For instance, while MO models have shown great performance on a variety of tasks, there's still work to be done in making them more robust to out-of-distribution data and more efficient in terms of computational resources. Moreover, as we push the boundaries of what AI can do, we also need to consider the ethical implications. As AI models become more powerful, we need to ensure they are used responsibly and that they are designed to respect users' privacy and autonomy. In conclusion, MO models represent a promising direction in AI, offering a powerful way to model diverse data and achieve impressive results. But as with all advancements in AI, they come with challenges that we must address to unlock their full potential. And that wraps up our deep dive into MO models. I hope you found it insightful and interesting. As always, if you have any questions or thoughts, don't hesitate to drop a comment below. And if you enjoyed this video and want to learn more about AI, make sure to hit the subscribe button. We have more AI-related videos coming your way, so stay tuned.